Hello and welcome back. We'll continue with Lesson 2, Part 2. In this lesson, our focus is on evaluating limits at infinity and one-sided limits. So together we went over some operations with infinity and we looked at limits at infinity in polynomial functions. We will now move on to limits at infinity in rational functions. And as a first example, I brought in the simplest rational function, y equals 1 over x. So the limit as x approaches infinity of 1 over x equals, by direct substitution, 1 over infinity. Divide by 1 by infinity, the answer is 0 plus. The limit as x approaches negative infinity, 1 over x is 1 over negative infinity, and that is 0 minus. Now, we'll move on to a more advanced example. So, the limit as x approaches infinity, negative 3 over x minus 2. Again, we'll try to substitute first, see if it works. So, negative infinity minus 2 equals infinity still, and a negative number divided by infinity will give 0, but a little bit less, so negative. Now, next example, the same function, but this time we're approaching negative infinity. Again, direct substitution, negative infinity for x, and then minus 2. So that's negative 3 over negative infinity. Negative 3 over negative infinity is 0. Because both signs are negative, 0 plus. In example number 4, we've brought in a variable to the numerator, and that will change the game a little bit. I'm going to try direct substitution and see if it works. So infinity plus 2 over infinity plus 5. That would be infinity over infinity. And we said that these are two undefined, extremely large quantities that we cannot compare or divide. So we're going to say it's not possible to evaluate this limit. So in other words, this is an indeterminate form limit. So we already know now, by now we know that, when a limit is in indeterminate form, that means that we have to use a different approach. And that's what we're going to do. Step number 1. We will factor the x of the highest power from both numerator and denominator. Okay. I wish the word numerator wasn't this long. Same goes for denominator. All right. So that means that we have the limit as x approaches infinity, and x is to the power of 1. 1 plus 2 over x. So x to the power 1 is the highest power there. The same thing works for denominator. And we have 1 plus 5 over x. Now we're allowed to simplify. We can simplify variables, obviously. We cannot simplify two undefined numbers, though, like infinity over infinity that we saw here. And that's the trick to choosing this strategy. So that's what makes this strategy work. So now we can directly substitute. And this will be 1 plus 0 plus over 1 plus 0 plus. So it would be 1 plus over 1 plus, which is equal to 1. So if we were to describe the steps, so you simplify. The common factor from both numerator and denominator, right? And last step, evaluate. All right, so we're going to take this idea to the next example. I would like you to stop the video and try it on your own. In the meantime, I will continue evaluating this limit. It seems very similar to what we went through in the previous example. And by a very quick inspection, I can tell that if I substitute infinity, or negative infinity for that matter, I will get an undefined expression. So it's an indeterminate form limit, which means that I have to factor out the variable of the highest power. The variable is x, and now we have 1 plus 2 over x over x, 1 plus 5 over x. So it's the same function, but now we're approaching negative infinity. So x simplifies, obviously, to leave us with 1 plus 2 over infinity, negative, over 1 minus 5 over infinity, negative. So this in return would equal 1 plus 2 over negative infinity is 0 minus, over 1, now negative, oh, that's a plus actually, so plus 0 minus again. So this would be number 1 slightly less than 1 over a number slightly less than 1. The answer is 1. Now we're going to take this idea to a bit more evolved rational function. So the limit as x approaches infinity of 2x4 minus x squared plus 8x over negative 5x4 plus 7. Okay, so same idea. We now know what it means to evaluate limits of rational functions at infinity. So we're going to take x of the highest power from both numerator and denominator. So we have x to the 4 here. And then 2 minus 1 over x squared plus 8 over x power 3. Denominator, we have x to the 4, negative 5 plus 7 over x to the power of 4. These two will simplify very nicely. And now we can directly substitute. So we have 2 minus 1 over infinity squared plus 8 over infinity cubed over negative 5 plus 7 over infinity to power 4. So this would be 2 minus 0 plus, and then plus 8 over infinity to power of 3. That's another 0 plus. And denominator will have negative 5 plus another 0 plus here. So basically we have 2 minus 0, 0 positive, so this would be a number slightly less than 2, divided by negative 5 plus 0 plus, it would be a number slightly bigger than, so to the right side of negative 5. The answer to this limit, for this limit, will be 2 over 5 negative. So you can place a negative anywhere you want, okay? Numerator, denominator in front of the fraction. All right, so we are moving on to the next example. So we have twisted this rational function in here by bringing in a square root. Now, think for a second. So how can we evaluate this? So we're going to get infinity over infinity again. All right, this is a bit tricky, but you can do it. Try to do this on your own. In the meantime, I will continue here. So I am going to take the limit as x approaches infinity. Now I'm going to take the greatest, or x to highest power out, and I have a square root in here, but for the moment being, I won't let the square root bother me, but I will take x squared out of the expression inside the bracket, so out of this. So this will give 3 plus 6 over x squared. And down in the denominator, I will take x out, and we have 5 over x, and then minus 2. Now notice how in the numerator we have 2 factors inside a root. So that's the same as if saying that we have the square root of x squared times the square root of 3 plus 6 over x squared over x, 5 over x minus 2. So x approaching infinity. The root of x squared is x, okay? We're approaching infinity, so we have no problem, or we shouldn't discuss the sign. It will be positive. So that would be x over x. And here we have 5 over x minus 2. And the numerator, 3 plus 6 over x squared. And now we can simplify x. That's what made our limit indeterminate. So now that's out of the way, out of our way. And we have limit as x approaches infinity. We are ready to substitute. And 3 plus 6 over infinity squared, square rooted, over 5 over infinity minus 2. That is not square rooted. So remember that 6 over infinity squared is a 0 plus. 5 over infinity is another 0 plus. So the answer would be root of 3, a little bit more than 3, divided by negative 2. A little bit more than negative 2 because we're adding 0 plus, okay? So in other words, we're going to say this is root 3 over 2 negative. That's it. We'll now continue with one-sided limits. If you remember the definition from the beginning of the lesson, one-sided limits describe the behavior or the value of a function as x approaches a specific value from both sides of it, from the left and the right side of it. So we're going to say the behavior or the value. Now, by one-sided limit, we mean the limit as x approaches a. A is that specific value, right? From the left side, and the limit as x approaches a from the right side here, okay? Left and right. So as an example, I brought in the function f of x equals 1 over x minus 2. So what we want to do here is find f of 2 first. So you know that if you substitute x by 2, that's how we find the value of a function at a point, then we're going to get 1 over 0. That's undefined. So we're going to say the function is undefined at 2. So we also know that just because a function is undefined at a point doesn't mean that the limit doesn't exist, right? So we're going to search for the limit as we approach 2, but we cannot let x equal exactly 2 because the function is undefined there. So in a situation like this, we approach the function from the left and the right side of number 2. So we can create an idea what the limit would equal. So when you approach 2 from the left side of it, then we have 1 over 2 from the left side minus 2. Now imagine that number 2 from the left is something like 1.99999, okay? So if that helps, you can write that down. And then minus 2. It seems that we end up here with almost 0, negative. And 1 over 0 negative is negative infinity. So in this case, we don't get a value for the limit, we get the behavior of the limit because the answer is negative infinity. And as you can see here, here is number 2. When we approach number 2 from the left side of it, the values of y are going all the way to negative infinity. We're going to do the same thing or something similar as x approaches 2 from the right side of it. So we're going to say this would be 1 over 2 from the right minus 2. Now when we say 2 from the right, we mean something like 2.0001 minus 2. So that would be 1 over a little bit more than 0, so to the right of 0. That's positive infinity. Now, as you can see here on the graph, as we approach 2 from the right side of it, all the values of y are going up towards infinity. Now, if we were asked to determine whether the limit at 2 exists, then we have to make that decision based on the left and the right hand limit. If the left hand limit equals the right hand limit, then we're going to say that the limit of the function equals whatever value the left and the right both equal. But as you notice in here, we are in a situation where the limit from the left doesn't equal the limit from the right. So in this case, we are going to say that the limit does not exist or is undefined. There is no limit for x equals 2 because we don't know exactly 2 if it is going to go all the way up or all the way down. So we're moving on to the next example. Remember that one-sided limits are typical in piecewise functions, and I brought in a piecewise function for analysis here. So here is the graph of it so that we can understand our limits better. The graph of this piecewise is made of the equations of these 3 pieces. Now each piece is defined in its own domain. So, oopsie, here. From -1 to 3, we have the rational function. And from 3 to 6, we have this portion of the graph. And from 6 to 10, we have this portion of the graph. I'm going to add a few more details in here. Now, from 6 to 10 means that 10 is not included, so I'm going to draw a circle, an empty circle here. And for x equals 6, the green graph is not defined, but the blue one is. Okay, so let me just actually match the colors. So the green is not defined, but the blue graph is defined. And between -1 and 3, so on -1, this is a point we want to include on the graph. And at 3, this is an empty circle. But this will be a full circle, okay? So we have to determine the following limits. We're going to start with limit as x approaches -1 first. 1, sorry. We're going to go 1 from the left, 1 from the right, and then based on the two-sided limits, we have to determine the limit at 1. So here is x equals 1. And when you approach 1 from the left side of it, the graph is going all the way down. So when you approach 1 from the left side, the graph is going towards negative infinity. So we're going to say negative infinity. You approach 1 from the right side of it, the values of y are going towards positive infinity. So since these two numbers do not equal each other, then we're going to say that at 1, the limit doesn't exist. So we're moving on to x equals 3. So we are going to approach number 3 from the left and the right side, and that will help us determine the limit at x equals 3. This is x equals 3 right here. Now, as we approach 3 from the left side of it, the values of y will be about this much. As you can see here, the values of y will be on the left side of it determined by 1 over x minus 1. So we're going to say that this will be 1 over 3 minus 1. And that would be 1/2. So that will be about 1/2. Okay? Now again, just to clarify, the reason why we chose to use the first equation when x approaches 3 from the left is because numbers 3 from the left side of it are in this domain, so that's where they are at. So when you move on to the next equation, these are all the numbers to the right of number 3. So when you find the limit as x approaches 3 plus, that's where you approach 3 from the right, the graph of the function will be up here. So we're going to say that the limit is about 4. Okay? Because we are approaching in this direction, and the graph is above the x-axis, so this blue graph. So then we're going to say that the limit from 3 plus is 4. As you can see, these are two different numbers, which makes the limit non-existent at 3. In the next example, we have the limit as x approaches 6 from the left and 6 from the right. Here goes number 6 again. When we approach 6 from the left, so 6 from the left, the graph is up here. So the values of y are approaching number 4. So we'll say that the value is 4. When we approach 6 from the right end of it, right side, or right hand, then the graph is in the green area, right? And the value of y would be approaching 4. Now, in this case, we see that the left and the right hand limit are equal to each other. So that tells us that the limit at 6 will be exactly 4. Okay, so we're going to move on to another example. So here we had the choice of using both the graphical and the algebraic representation of